Hi, this is Debojit Das, and today I'm here to present my paper on budgeted combinatorial multi-arm bandits. So, what is a multi-arm bandit? A multi-arm bandit, in its basic sense, it has a set of available arms, which are called the bandits, and each arm, when pulled, generates a reward from an unknown distribution. The typical goal when designing an algorithm for a multi-arm bandit is to optimally pull one arm in each round while also learning the mean of the reward distributions and maximizing the earned reward. The problem here lies in the fact that since we don't know anything about the arms initially, if let's say an arm seems to be promising at first, it is not necessary that that arm is actually the optimal arm. Sometimes it is a better idea to explore other arms and as we explore, as we get more information, we will slowly converge on the optimal arm. However, this might lead to a lot of exploration, which means that we will eventually end up with a lower reward than what we could have had. This is called the exploration exploitation dilemma, and this is the basis behind multi-arm bandit problems. Multi-arm bandit problems have a lot of applications in daily life, in our regular life, right? But most of the places where we would use it, we also have certain other constraints, certain other requirements that need to be met. So we end up with certain variants of the vanilla multi-arm bandit problems. Take this example, right? So you're a manager and you have workers working for you. Now you want to do this one task several times. You need this one job to be done several times, right? Now you can assign workers to these tasks in such a way that the utility that you get from each task is maximized. The overall utility across all tasks, you want to maximize that. Now, all these workers, they refuse to work for free. They have a certain cost and you have a budget, and you can only select workers such that your budget constraints are met. These tasks, while you can always select one worker, it is sometimes a much better idea to select a set of workers so that these jobs are done better. They're done with higher efficiency. So we started with a normal multi-arm bandit situation, but we ended up with a setting where you have budget constraints as well as you can have a combinatorial setting. So that is the basis of our paper. That is why our paper is on the budgeted combinatorial multi-arm bandits. Such a scenario is what we hope to deal with efficiently. Now, of course, a lot of work has been done in the past on budgeted bandits as well as combinatorial bandits. Starting with this paper, Bandits with Knapsacks. This deals with multi-arm bandits which have several budget constraints, several resources, each having a budget constraint. The problem here is that they only deal with the single pull setting. That is not enough for us. The paper, a multi-arm bandit based incentive mechanism for a subset selection of customers for demand response and smart grids. This involves subset selection. However, there are no budget constraints. That is once again not useful for us. Papers like contextual combinatorial multi-arm bandits with volatile arms and submodel rewards and budget constrained multi-arm bandits with multiple plays, they have combinatorial frameworks with budget constraints. However, they have this innate assumption that a superarm can only be of fixed size. This paper that was the closest to us was the combinatorial semi-bandits with knapsacks. They have a similar setting to us where they have a budgeted combinatorial multi-arm bandit setting with an overall budget and no restrictions on the size of the superarm. However, they approach this by distributing the budget uniformly over all rounds, and hence they end up with a regret of order root t log t, which is higher than what we achieve. We achieve a regret of order log square t. So let us talk about our framework. We have a set of arms in our multi-arm bandit. Each arm has a stochastic reward distribution with which is fixed but unknown, with unknown mean values mu I. Each arm, when pulled further, incurs a cost which is known to us. We play this multi-arm bandit game for T rounds, and we initially have a budget of B. Now we consider an additive setting, which means that the reward of the super arm is basically the sum of the reward of each arm, in the super arm. We also consider semi-bandit feedback. The goal of an algorithm in our setting will be to maximize the total expected reward obtained over all T rounds within our budget constraints. We formulate our problem in the form of an integer programming as follows. Here, the first constraint is the budget constraint. The second constraint is the number of turns, and the objective that we want to maximize is the total reward. Having stated the problem, now we try to solve it. We have two approaches in our paper. The first one being a greedy approach. Here we first solve the offline setting, where we assume that we know the mean values. We reduce our problem to a knapsack problem where each arm has T copies, and the goal is now to select a subset of these NT arms available so that we maximize the reward subject to our budget constraints. The key idea here is to select arms greedily using their bank per buck ratio. To solve the online setting, however, we apply the algorithm from the previous slide at every turn. At the start of each round, we apply it on the remaining budget and the remaining number of tasks. From this, we get the number of times each arm should be selected. The key idea is that if the offline solution does not select an arm even once, it either has very low bang per buck ratio or it has a very high cost higher than the remaining budget. In either case, we do not want to. The second approach that we use involves a linear programming solution. We reduce our combinatorial setting to a linear setting that was presented in the paper Bandits with Knapsack. Once again, we first solve the offline setting, which means that we know all the mean values. The new setting has T rounds with every round consisting of N plays. On the ith play, our algorithm can choose whether to pull the ith arm or to not pull any arm. The setting is thus transformed into a single pull setting with N into T rounds, where it is not required to pull an arm in every round. We additionally model each arm as a resource, and pulling an arm necessarily consumes 1 unit of the resource. The maximum you can consume is T, which basically means that you cannot pull an arm more than T times. The key idea is the key idea in the online setting is once again to greedily select the arms based on their bang per buck ratio, pretty similar to what we did in our greedy approach. Our main result is this theorem, which says that our LP algorithm achieves a regret of order log squared T. This is a lot better than the previous existing results, which the best previous existing result achieved a regret of order root T log T using this algorithm called semi-BWK-RRS. We will compare our algorithms with the performance of semi-BWK-RRS in the next few slides. We perform experiments on our LP algorithm, our greedy algorithm, and the algorithm semi-BWK-RRS, which was the best known result until our paper. We compare these three algorithms on a few different parameters. So the first thing that we check is for these values for fixed T, we study the effect of budget on regret. As we can see, on increasing budget, regret initially increases, and then after a certain point, the regret starts decreasing and goes down to 0. This is because regardless of whether we know the values beforehand or we don't, uh, the optimal algorithm will always select every single arm for every single task, provided the budget is high enough. Hence, the regret will drop down to zero at some point. As we can see from the graph, our greedy algorithm performs a lot better than both the other algorithms, and even our LP algorithm performs substantially better than that of semi-BWK-RRS. Next we evaluate our performance on fixed budget, and we study the effect of increased rounds on regret. As we can once again see, our greedy and LP algorithms perform a lot better than semi-BWK-RRS, and at the gap only seems to be increasing. Next, we fix the budget per round ratio to be this, and we study the effect of increasing task and proportional budget increase on regret. We normalize it with respect to the greedy algorithm, and we see that even the LP algorithm, which is not as good as greedy, but it still outperforms semi-BWK RRS by a big margin. Finally, we conduct an experiment where the arms are not identically distributed, and what we see is that our algorithm perform both our algorithms perform a lot better than that of semi BWK RRS. This is because they fix the budget per round, and if we take such situations where it's not uniformly distributed, then our algorithm clearly shows the edge. Concluding our presentation, we showed that the existing literature has either considered a fixed number of pulls or a fixed predetermined budget. We we handle a more general case. We propose two algorithms and compare our work with the previous best work. Please scan the code to see the slides till the presentation. Thank you. Any questions?